we have that mg sine theta is equal to 12.5 kilograms times 9.80 meters per second squared times sine of 10 degrees. Multiplying that out, we get 21.3 newtons. What about the largest value that the frictional force can have, Fs max? We know Fs max is mu s times the normal force. But for the incline, remember, the normal force is mg cos theta. So this becomes mu s times mg cos theta, which we have as 0.210 times 12.5 kilograms times 9.80 meters per second squared times cosine of 10 degrees. Multiplying those out, we get 25.3 newtons. Let me ask you, what happens? Does the mass slide or not? The force down the incline is 21.3 newtons. Fs max, the maximum value of the frictional force, 25.3 newtons. Notice the frictional force, the maximum frictional force, is larger than the force down the incline. The friction is strong enough to keep the object stationary. It does not slide. It remains stationary. And so our final answer is then the acceleration is what? 0. The block does not move. Very, very good. Excellent. Let's think about this. If the incline were larger, so let me just show you. So this would be an example where we have, put it this way like this, we have a small angle and the block does not slide. The angle is small enough, there is enough friction that the block remains stationary. If we were to actually increase this angle, eventually we get to a point where the block starts to slide. Let's ask ourselves, what is the maximum angle? This one? Go a little further, 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 further. What's the maximum angle at which we can put the incline and have the block not move? But if we were to put it a little bit higher, it does slide. What's that maximum angle? We might call it theta max. Well, how would we find that? Well, that would be where the force down the incline just can be balanced by Fs max. In other words, where mg sine theta is just equal to mu s Fn. In other words, mu s mg cos theta. If it were a steeper angle, then the force down the incline would be larger than Fs max and the block would slide. But right at that maximum angle, where mg sine theta was equal to mu s mg cos theta, that would be the maximum angle that we could have. Well, let's figure out, what is that angle? Setting mu s mg cos theta, which is Fs max, equal to mg sine theta. Let's just remember, what are these quantities? Mu s mg cos theta, that is Fs max. Mg sine theta, what's that? That is W sub x. We're comparing the force down the incline, the component of the weight acting down the incline, with Fs max, the maximum value of the frictional force. When those are equal, that's just the maximum angle that we can have. When this side is bigger than this side, it remains, the object will be stationary. When this side is bigger than that side, the object starts to slide. When they're just balanced, they're just equal to each other, that's the maximum angle which will keep the object stationary. Dividing both sides by mg cos theta, we have mu s, canceling out the mg cos theta, equals mg sine theta divided by mg cos theta. We notice the mg cancels the mg, and what are we left with? Sine theta over cos theta. What is sine theta over cos theta? That is tan theta. So, when mu s equals tan theta max, or theta max is equal to the inverse tangent of mu sub s, that gives us the maximum angle that we can incline our surface. Well, what do we have in this case? We have that μs is 0.210. What's our maximum angle for this particular problem? Well, if we take the inverse tan of μs 0.210, what do we get? It turns out that we get 11.9 degrees. The maximum angle that we could put our incline is 11.9 degrees, and that would still just barely keep the object stationary. What angle did we have for our problem? Well, we had a 10-degree angle. Obviously 10 degrees is less than 11.9, so yes, the object will, the block will remain stationary. What we need to do is, let's try looking at an angle that's larger than 11.9 degrees and see what happens in that case. Well, we know what's going to happen, we know it's going to slide, but let's go through it and verify that. Let's imagine we've now increased our angle to 40 degrees. So rather than 10 degrees, 40 degrees. What do we get in this case? Well, mg sine theta, the component of the weight down the incline, again, 12.5 times 9.8, but now sine of 40 degrees. What does that give us? That gives us 78.7 newtons. And what about the frictional force, Fs max? Again, μs times Fn, μs times mg cos theta, 0.210, 12.5, 9.8, but now cosine 40 degrees, multiply that out, and what do we get? In this case, we get 19.7 newtons. Notice, our force down the incline is larger than our maximum static frictional force. The friction is not strong enough to keep the block in place. So what does it do? It starts to slide. What kind of friction do we have? Kinetic. So now we need to look at the kinetic frictional force, which is mu k times the normal force. Again, mu k times the normal force, mg cos theta. So we've got 0.12, 12.5, 9.8, cos 40 degrees. Remember, we've got to change that angle from 10 degrees to 40 degrees. And all of these equations, multiply this out and we get 11.3 newtons. What is now the net force in the x direction? What forces are in the x direction? We have W sub x. Well, we already know what that is, 78.7 newtons. And then what? Well, the normal force is in the y direction. We don't need to worry about that. The frictional force is in the negative x direction. It's the kinetic frictional force, which we know is 11.3, so minus 11.3 newtons. Those are all of the forces in the x direction. We subtract those, and what do we get? 67.4 newtons. And we know that must equal the mass times the acceleration in the x direction, leaving us with a sub x is equal to 67.4 newtons divided by the mass, which is 12.5 kilograms. Dividing that out, and what do we have? We have the acceleration in the x direction is 5.39 meters per second squared. There we go. There is our final acceleration. 5.39 meters per second squared. The block is accelerating downward at 5.39 meters per second squared. Excellent. Let's take a look at some other problems using friction and Newton's laws and trying to figure out are they static problems or dynamic problems. Let's imagine that we've got a crate on the back of a flatbed truck. And this truck is going to start to accelerate to the right. So the truck accelerates this way. Now what's going to happen? The truck needs to accelerate the crate along with it. The crate needs to maintain the same acceleration with the truck. If the crate cannot maintain that acceleration, what's going to happen? It's going to slide off the truck. Another way of thinking about it is the truck will slide out from underneath the crate. Let me give you a little example. So let's imagine this is the back of the truck, and here's the crate, say, on the back. if the truck accelerates slowly, the crate stays on the back. But if the truck accelerates too quickly, there's not enough force to keep the mass, the crate, accelerating with the truck. It slides off the back. Well, let's figure out how fast can that truck accelerate and keep that crate on the back. Let's assume that we have, well, before I tell you, what kind of force is actually going to accelerate the crate? What force is it that's accelerating the crate? Well, it's a frictional force. What kind of friction? Well, you might think the crate is moving, so it must be kinetic friction. But actually, what we want is the crate to not slide on the truck. And if the crate is not sliding, what kind of friction is that? It's static friction. What direction is the frictional force acting? Well, it's the frictional force that is accelerating the crate. What direction is the crate accelerating? We want the crate to accelerate in the same direction that the truck is. So the acceleration of the crate we want to also be to the right. And if the crate is accelerating to the right, what must be the direction of the force? The force must be to the right. So the force that's acting on the crate must be static friction, and it must be to the right. What's the maximum acceleration that the truck can have? Well, what's the maximum acceleration the crate can have? The crate will have its maximum acceleration when the maximum amount of force is applied to it. What's the maximum frictional force that can be applied to the crate? Fs max. There we go. So we're going to have the forces. I've started the free body diagram over here. What forces are acting on the crate? We've got the weight, which is mg. Let's assume that the mass of the crate is some mass m. We won't stick that in there yet, or at all if we don't need to. And let's assume that we have a coefficient of static friction of, let's say mu s is 0.170. So that's the coefficient of static friction in between the crate and the surface. The forces are then the weight, which is mg, the normal force, which is vertically upwards, the frictional force, which we know is going to be to the right. And to figure out the maximum acceleration for the crate, likewise for the truck, what's the maximum acceleration the truck can have without the crate sliding off the back, we'll assume we have the maximum force being applied to the crate, which is Fs max. There we go. We know then the normal force balances the weight, so the normal force is mg. Fs max is mu s times the normal force, with the normal force equal to mg. In this case, we have Fs max equals mu s mg. That's the force acting on the crate, the maximum amount of force. We want that to then equal the mass of the crate times its acceleration. So we'll say that this equals the mass of the crate times its acceleration. We can then solve for the acceleration, divide by m, and we have a equals mu s times g. The acceleration doesn't even depend on the mass. We don't need to stick the mass in there. What do we get for the acceleration? It is mu s 0.170 times g 9.80 meters per second squared. We multiply that out and we get A is 1.67 meters per second squared. What does that tell us? If the truck accelerates at a rate less than that, let's say the truck accelerates at 1.50 meters per second squared, what happens? There's enough friction to accelerate the crate stays on the truck. What if the truck were to accelerate at 1.80 meters per second squared? Well, in that case, the crate does not have enough friction to accelerate it, and what will happen? The truck will slide out from under the crate and the crate will fall off the back. Very, very good. Let's take a look at a similar kind of problem, but let's imagine the truck is actually going up a hill, going up an incline. How does that affect the acceleration that the truck can have and still keep that crate on the back?